Hello, welcome back to Einstein Mechanics once again. Today marks the episode 2 on chapter 2, and we are looking at statically indeterminate structures. So, in the first episode, we talked about structures which are fixed at one end and loaded axially. But in this case, we are going to look at bars which are fixed at both ends. So, the bar is not going to expand or is not going to elongate outside the fixed ends. It is restricted. So expansion is quite difficult. So let's consider this bar, which has two fixed ends, and it is labeled A, C, and what? And B. And a force of P is induced inside the bar. It has a uniform what? Cross-section area. And we can see that from A to C is labeled as A, small a, and from C to B is labeled as small b, and the total length is given. So now the free body diagram, we have to detach this bar from its fixed end, and this is what we see. This is the force P induced inside the bar, and there is a reaction. Since there is a fixed end, as we remove it, we have to indicate the directions of the reaction. And as we go by, this force is looking in the opposite direction to the reaction. So I can call this as my RA, and the reaction at B as my what? RB. The lengths are there. So there's two unknowns here. Look, there's reaction at A and reaction at B. P will be given to us so that we know the force induced in the material. And from the summation of forces on the vertical, we can know that, or summation of forces on the vertical, they all sum to what? 0. And looking at this diagram, we can say RA plus RB should be equal to what? P. So the summation of RA and RB will give us what? P. Therefore, RA plus RB minus P should be what? 0. As one equation. And here we can see that two unknowns, RA and RB, but one equation, which will make it impossible for us to find the reaction. What do we do here? We have to find a way of getting another equation that we can solve for the two unknowns. So what do we consider? Let's look at the bar. As we can see, this bar cannot elongate outside the scope. So assuming if I divide this bar into two, the top being A and the down being B, do you agree that as the A elongates, it is going to contract the B, and as the B elongates, it is going to contract the A? That's how it works in this type of what? Structures. Because it is fixed, there's no movement outside its scope. So if A is expanding or elongating, there will be a contraction in B. So at the end, the summation of the individual elongation will be what? 0. Are we good? So elongation, let's look at this bar in A, or from A to C, plus whatever happens, this can mean elongation or contraction in C to B will result in what? 0. Because if it expands by 2 meters in AC, it is going to contract by 2 meters. And we are going to see that 2 minus the 2 is going to give us what? 0. Are we good? Meaning at the end, the total elongation from A to B will be 0. And we can play with this diagram to get the reaction, whatever happens here, whatever happens here. And we can get a beautiful equation for equation 2 so that we solve for the two unknowns. We are going to solve some examples related to such bars so that we know how to go by the reactions and getting our two equations. And it's quite interesting. So let's get started. Let's look at this example 2.3. The axially loaded bar ABCD shown in the figure is held between two rigid supports. The bar has a cross-section area A0 from A to C, and it has 2A0 from C to D. Obtain formulas for the reaction RA and what? RD at the end of the bar. Then we determine the displacement, that's change in B, or the elongation at B and the elongation at what? C, the point B and C. Okay, so what do we do here? It's interesting. We have to apply the idea of indeterminate what? Structures, meaning they are fixed at their ends. And what do we know? We know that we have to check out for the reactions and then look out for the elongation as well. So from this, we can draw a free body diagram, and I'm going to have it like this. Sorry, this is my free body diagram. This is the base. Okay, so what happens? We are going to have this force P here, this force P at the point B. It is induced in the system or the bar at this point P. And what again? Here is A, there is B, C, and D. The length from A to B is L on 4. Then the length from B to C is also L on 4. The length from C to D is L on 2. Very good. And we have the area, the smaller area as A0, and the area here as 2A0. Then let's try to bring our reactions at the end. Since this fixed end is removed, I'm going to draw in direction to this, and from this place it is, and reaction is going to be in the opposite direction to that, and this is what I'm getting. So reaction at D and at the A's, the reaction is going to be in the opposite direction, which is reaction at A. Very good. So now we have our free body diagram, we have all our parameters. What do we do? Let's sum the forces along the x, because this is, and they are all going to sum up towards 0. So looking at the direction of the forces, can we say that RA, the reaction at A, and the reaction at D minus P is going to give us 0? Yes. Now we have our first equation. We cannot determine these two unknowns unless we get another equation too. So we are going to consider the elongation. As we know that the total elongation from A to D, elongation from A to D in the bar is going to be 0, because as this is expanding, this will be contracting and they will cancel out. So let's look at what happens in individual bars. So this is divided into 3, A to B, B to C, and C to D. So I'm taking at AB, what happens? When I section AB, I'm going to get this free body diagram over there. From A to B, I'm having this reaction here, RA, and I'm going to section this, meaning I'm going to get another reaction here, what? RA, in what? AB. That's what I'm getting. And we know that elongation in AB is going to give us the force, which is RA now, by what? The length. Are we good? The length in AB, or the length in, sure, AB, but the length, is what? Over 4. Since the length of AB is L on 4, divided by the area is A0 and E. So it is going to give us RAL on 4A naught E. That's the elongation that happens in the AB. Let's take the BC. If I take at BC, this is what happens. I'm going to section BC, and if I create a cut in BC, I'm going to get the bar in this form. So let's assume this is B, this is C, this is D, and there is a force here. So I want to section what? BC and see what actually happens in what? In BC. So if I section this, meaning this force is not going to appear again. This P is not going to appear, but I have this reaction over there, RD. So I'm going to get this half part of the BC as that. So there will be a reaction here that will be opposing the RD in the region of what? BC. So this, I'll consider the right hand side and know that as I section here, this force is going to be like the opposite one, so RD. And it is a compressive force. It is compressing the bar. So at BC, I'm also getting the elongation at BC to be equal to the same reaction RD, and the length. What is the length of BC? L on 4. So it is going to be 4 times A naught E. And the same thing, the last part, I'm going to consider CD. And at CD, what happens? I'm also going to get a cut, the bigger side like this. So there is this reaction over there. RD is still there. RD, RD. But this is symbol CD, segment CD. It's still compressive force inside the bar, meaning elongation at what? CD is going to give me the force, which is still RD, multiplying the length. The length is L on 2, so it's going to be L 2AE. Are we good? All the area here is what? 2A naught, but this one is what? Divided by 2. 2. So finally, I'm going to get elongation, which implies the elongation in CD is going to give me RD. L, the area here in CD is 2A naught already, and the L is still over 2, meaning I'm going to still get 4A naught E. So I have this reaction, I have that, and I have that, meaning the elongation, total elongation from A to D is going to give me elongation at AB, which was a tensor elongation positive. The BC was compressive negative, CD was compressive negative. So it's going to be minus elongation in BC minus elongation in what? CD. And we are going to bring their formulas here. So the total elongation from A to D is now going to give me, from A to B is RAL on 4A naught E minus at BC was RD L on 4A naught E, and the last one is still compressive RDL on 4A naught E. We are having this as our total elongation, and it's equal to 0. Very good, because at the end this is going to cancel out and it's going to be 0. So we can equate, and looking at this, we have common denominator. What can we do? We can choose the top one. It's a simple mathematics. When you have a common denominator, adding or subtracting, you can just play with the numerator. So I'm going to take the numerator RAL minus RDL minus RDL is what? It's going to give me 0. Since the total elongation, it is fixed, all the elongation in A, B, and C are going to end up being what? 0. I have a common length, so the length can also what? Cancel. I can divide both sides or the terms by L, and we're going to get reaction at A minus, this is RD, 2 RD at D is equal to what? 0, meaning RA is equal to 2 times RD. I have my equation what? 2. Are we good? Now we can bring equation 2 RA into equation 1 and find for them in terms of what? P, because P is the only force acting in the bar that we know the magnitude. So we can play with them to get what? P. Meaning if I bring equation 2 into equation what? 1, I'm going to get RA plus 2 times what? Or I'm going to replace RA by this, which is from equation 1. I'm going to get 2RD plus RD is going to give us what? Is going to give us P, meaning RD is equal to P on 3. RD is P on 3. So when I put RD in this equation, I'm going to get RA, you can try it, to be 2 on 3 P. So these are the reactions. So therefore at A, the reactions are this and that, meaning RD is equal to P on 3 and RA is equal to 2 on 3 P. We are done with the A part. The B part said, determine the displacement B and the displacement at C so that we know what is happening in the bar. So we want to find out the displacement happening at B and what is happening at what? C. So let's start that one. So the B part, determine the displacement at B and at what? At C. What do we do? So we want what is going to happen in what? AB, because anything that is happening at B is as a result of the force at P causing it to what? To happen. And anything happening at C is a result of something happening in what? The entire CD. So I can boldly say that elongation at B is the same as elongation from A to what? B, which I know the formula as force in AB multiplying the length of AB, the area of AB, and the E. Are we good? Yes. So let's look at what is going to happen. And so elongation at B in AB, what is happening? We know that the force in AB from the free body diagram we drew, the force was what? RA. It was RA, so RA, and the length at AB is what? L on 4 on the area at AB, then the E. But looking at this, the R in terms of P, we got RA to be what? 2 on 3P multiplying L on 4 over. We can replace the area as just A naught E. So playing with this, we are going to get elongation at B, which is what is happening in AB as P on L on 6 A naught E. So this is the displacement at B. Then at C, I can also say displacement at C is the same as from C to what? D, since it is a continuous bar. A to B is also what? Continuous. Going to be C to what? D, which is giving us the same thing, a force in what? CD multiplying the length of CD on area of CD times the E. What do we have? The force in CD from the free body diagram was what? RD multiplying what is the length? L on 2. What is the area? It is 2 times A naught. We have our E. But from the deduction, we got what is RD in terms of P. RD in terms of what? P, which is P on 3. It was P on 3 multiplying L on 2 on 2A naught by E. So this is what we are getting here. When we play with that, we are going to get PL on 12A naught E. So this is the displacement at C, or the change in length at C, and we are good to go. This question is now solved. We can proceed to the other question or the other slide. Strain energy. So there is a concept also under this topic or a subtopic called the strain energy. And we know that the strain energy of an axial loaded bar is given as U. We represent the strain energy as U, where U is equal to P square L over 2EA. So the strain energy, the energy caused as a result of strain inside the bar is given as P square L on 2 times EA for bars. So we have the strain energy for a bar. What if it is a spring? We can replace it by the constant K. We know that for a spring, the spring constant K is given as EA over L. This is the spring constant. And we can see that we have L on EA. So can we say the inverse of K is L on EA as comparing to this? So therefore, for springs, the U, the strain energy for springs, can also be P square on 2K, where K is the spring constant. Where K is the spring constant. We'll be solving a lot of examples under this spring constant, and we are going to see how it is going to help us. Okay, so we have this example. This is interesting. we have this example under strain energy. So we have a bar ABC, which is shown. We have the forces P and what Q on the bar. We have the E also and the A. Now the question is asking us that this structure, we should determine the strain energy U1 of the bar when the force P acts alone. So we should assume that this bar is being acted alone by the force P, where we are going to neglect the Q and find the strain energy, what is actually happening inside the bar. So now I can draw my free body diagram for this bar and I can see it in this way. Because the question is saying Q is 0, I neglect Q, and this is the P. It is going to have a reaction what? P over there. P. Are we good? Okay. We have a reaction P. And as P is acting, it is going to act. Whatever P is causing in this bar will cause through the total what bar. Look at this, because it is at the end. If it is stretching, it is going to cause a strain inside the bar from A to C. So it is taking all the bar. Are we good? I know why I'm saying that we will consider the Q and we will see what happens. So for the P, it is stretching the whole bar. Are we good? All right, so we consider the force to be what? P, and we have our rigidity EA. And simple, we can know that the strain energy, so the strain energy when force P acts alone, so U1 can be the force. What is the force on this bar? The only force is P. So we are going to get the P squared. What is the length of the bar? The length of the bar is half the length plus half of the length, which is the total length L. P square L, and the formula is 2 area E. The area E was given here, and we have 2 times of it, meaning the strain energy U1 when the force P acts alone is going to be P square L 2AE. It's the same as the formula. So B, when Q acts alone, now Q is going to act alone. Let's look at what is going to happen and draw a free body diagram for that. But what are we seeing? Let's look at this. Q is acting alone, no P. Are we good? If Q is causing something, let's look at us. Let's see if this point is being stretched. Its effect is going to happen here. We are going to see its effects. The strain. Let's assume a force. Yeah, Q is a force, and we are pulling from A to B. The effect is going to happen only in A and B, looking at the point of application of the force. So it is going to happen in half the length. So we can say our internal or our strain energy U2 when Q acts alone. What force is acting on the bar now? Q square, or is Q. So we are going to have Q square times the length, and the effect of Q is going to be on half the length, multiplying half the length over 2 times AE. And when we play with this, we are going to get the U2 to be Q square L on 4 times AE. So we are done with the A part and the B part. Now we are to determine the new strain energy when the force P and Q act simultaneously upon the bar. And one thing we have to know is that we know that if there is a strain or there is an elongation in AB and there's an elongation in BC, the total elongation is going to be AB, elongation in AB plus elongation in what? BC. The same thing happens to the strain energy. If there's a strain energy U1 here and there's a strain energy U2 here, the total strain energy is going to be U1 plus U2. Are we good? So the addition of the individual strain energies is going to give the total strain energy. So let's look at when P and Q are working, or these two forces are in position, what actually happens to the U? So we know that our total strain energy is going to be the strain energy in AB plus the strain energy in what? BC. So I can represent them by a formula UT, and know that it is always the force square in what? AB. We are yet to deduce the forces. We'll come back. We are just writing the formula. The length in AB to 2 times the area E plus, here we can say P square BC, the length of BC, and 2 times AE. Then we are good to go. But what is happening when these two forces Q and P are in position? Let's draw the free body diagram. We can see that this is the free body diagram, and Q is in position. P is also in position. We have, therefore, there's going to be a reaction opposing this force. Let's call it what? X. Are we good? We are going to call it X. And here is A, B, and C. So I really want to see what is happening there. U1 inside the AB. I'll make a cut. From this, we can sum the forces. Can we say X now is equal to P plus Q? Yes, because X is opposing the direction of P and Q. So to keep it in equilibrium, X is equal to P plus what? Q. So U in the AB, U in the AB is going to be, if I make a section through AB, I'm going to get the force X, where X is a what? P and what? Q. So the force now in AB is going to P and Q, remember, square. The length of AB is now going to be L on 2 over 2A. This can further be expanded as what? P square plus 2PQ plus Q square. We can multiply by the length, or on 4AE. That's what's going to happen in what? AB, the U. Now let's look at the U happening in what? BC. When I make a section through BC, I'm going to take the right hand side, and this force is going to be the force being induced in what? BC. So, and the force is P. So I'm going to get the force P square. What is the length? It's also L on 2. And when I make it simple, I'm going to get L for AE. Are we good? So I can now sum these two equations, since the total energy is the summation of both. So now the total U is going to be P square plus 2PQ plus Q square multiplying the length. The whole thing is multiplying the length on 4AE plus P square L on 4AE. Now I can play with this. So I'm going to play with this, then I'm going to get ut should be equal to, I can bring 1 over 4 AE out, leaving p squared. This L is going to multiply through, plus 2p q L plus q square L. And we are also going to have this p square L. And we can also go further to see that this is going to give us 1 over 4 AE, and we are going to have 2 times, since the p square is 2, 2 times p square L plus 2 times p q. Very good. So meaning if p and q are acting simultaneously on the bar, this is going to be the total strain energy, the total strain energy induced in the bar. So if you have the values of the force and the length, you just plug them in, then you calculate for the ut. Okay, so in this example, we have a high strength steel rod with diameter. So the diameter is 25 millimeters, which is 0.025 meters. We have our E to be 200 gigapascal, and it must transmit a tensile force, that's the P, to be 134 kilonewtons. Now, if the length L of the rod is 1, what is the final length? So what is the final length of this steel rod? And we know that always final length, which is L2, should be the L1 plus the elongation produced in the bar. Very good. All right, so since we have our D, can we calculate for our A? So the area here now is going to be pi d squared, and our D is 0.25 square on 4, where I'm going to get 4.908 meter square. And what do we do? Looking at this bar, we are to find the elongation. Since it is in what? Tension, there's going to be an elongation. And our elongation in this bar now is going to be PL over what? AE. So we have our P to be 134 kilo, and our length, if the length is 1 meter, so our L is 1 meter by 1. On our A, the area is 4.908, and our E is what? 200. 200. Therefore, our change in length is going to be 0.001365 what? Meters. But the question said we should what? Find the final length. Therefore, final length L2 is L1 plus the deflection, which is going to be 1 meter plus 0.001365 meters, meaning our final length L2 will be 1.001365 meters. Very good. B. What is the ratio of the length of the rod to the increase in length? So B part is acting as the ratio of the length of the rod L or L1 to the increase in length, the deflection. That was the increase in length. So now this ratio is going to give us 1 on 0.01365 0.01365, and the ratio is going to be 730 watts. 7, no units. Now the C part, if the increase in length is limited to 3.8 millimeters, what is the maximum load that can be permitted? Now they are asking us that if the increase in length, that's the elongation, is now 3.8 millimeters, 3.8 millimeters, what will be the P maximum, or what P are we going to what get? And I'm going to convert this to what meters to be 3.8 10 raised to the power negative 3 watts meters. And I know that elongation is always the force L on what AE. So now they are telling me that what would be P if the elongation is this. So I'm going to say P is equal to elongation AE on L. Therefore, P will be elongation given 3.8 times 10 negative 3. The area is what? 4.908 10 negative 4, multiplying the E, which is 200 over L, which is 1. So my P max is going to give me 373 kilonewton. So if the increase in length is limited to 3.8, the maximum load or force P is going to be 373 kilonewtons. That's the end of this problem. Alright, so let's look at this problem. A prismatic bar AD is subjected to load P1, P2, P3, and they are acting at the point BC and what D respectively. We have the figure there. Each segment of the bar is 500 millimeter long, and the cross-section area is given as 900 millimeter square, and it's made of copper with E 120 gigapascal. Determine the displacement D at the free end of the bar. Wow, this is quite interesting. So we have this bar under these various internal what forces, and the question is asking us to find the displacement, virtually the elongation that is going to happen at the end D. So as we know, we are going to find the elongation in each segment, then add them to get the total elongation. So since we have previous knowledge in this, it's going to be very fast here. First, we have to draw the free body diagram and know the reaction at the end. And if I'm to draw the free body diagram for this, I'm going to get something like this. So I have this point B and this point what? C. And C has a force P2. There's a force P3 here, and there's a force P1. And I'm going to get a reaction R. This A, B, C, and what? D. So looking at the diagram, or somebody can choose the reaction to be in the opposite direction to this. Yeah, that's what I've been doing, but we will see that you are going to get a negative, meaning it is going to reverse. So assuming I'm choosing this reaction initially because I know it is going to oppose this force as my R, I'm going to get the summation here to be R. We are using this diagram to what? Calculate for the reaction R. So R plus, you can see P2 plus P3. They are all in the same direction, should be equal to P1. So meaning R should be P1 minus P2 minus P3. And what are the values? R is equal to P1 is, from the question, P1 is 13 kilonewton. 13, they are all in kilo. P2 is what? 13, and P3 is what? 50. So I'm getting my R to be negative 50 kilonewton. And this negative is telling you that the direction I chose is in the opposite ones. That's why I first made this. So actually the R is what? In the direction of P1. So it's going to be positive. So we are going to take the positive one, 50 kilonewtons. Are we good? So let's find the elongation at AB. What is happening? If I make a section in AB, this is what I'm going to see. I have my R here, and it's also going to give me an R here. That's for what? AB, if I cut through. And I know the value of R to be what? 50 kilonewtons. I know the length of what? AB to be 500 millimeter, which is what? 0.5. Each of the segments length is what? 0.5. And I have the area to be what? Constant. A is giving us 900 millimeter what? Square. So 900 millimeter square, you're going to divide by what? 1000 square. 1000 square, which is going to give me 9 times 10 negative 4 meter square. So elongation at AB is going to be the force R, which is 50 kilo, multiplying the length. The length is 0.5. The AE, the E is 9 times 10 negative 4. And the E is copper 120 giga. So elongation in AB is going to give me 2.395 negative 4 meter. It is positive because it is in what? Tension. Let's look at BC. Elongation in BC. When I draw a free body diagram for BC, I'm getting something like this. I'm cutting BC. I have this force here, P2 there, and I have this force P3 also there, and this is going to oppose P2 the reaction. And I know that R will be equal to P2 plus what? P3, and P2 is 13. R will be 13 plus what? 50, and I'm getting 63 kilonewtons. So my R in BC is 63 kilonewton. Therefore, my elongation in BC is going to be 63 kilo, multiplying the length is also 0.5. On my area, the same cross section, so 9 raised to the power for the same E, 120. My elongation BC is going to give me, for the BC, the elongation is 2.9. You can check with your calculator and see 10 negative what? 4 meters. Let's look at what happens in what? The last segment, CD. So elongation in what? CD. If I make a free body diagram for the CD, I'm getting something like this. And the force acting is what? P3. It's going to also have a reaction what? P3. So R is equal to P3, which is equal to what? 50 kilonewton, which is the same as the first AB. It also had a force of what? 50 kilo. So meaning elongation in CD is also going to be the same here, because the same 50 times the same length over the same 10, and we are getting 2.395 times 10 negative 4 meters. Meaning the displacement at the D, which is the total displacement, is going to be displacement at AB. They were all in tensile, so positive, positive. Elongation in BC plus elongation in what? CD. And upon adding this, that, and that, the total elongation produced will be 7.5466 to the power negative 4 meter. So meaning the displacement at D will now be 7.5466 10 raised to the power negative 4 meter. Let's look at the B part. The B part is saying what should be the load P3 if it is desired to reduce the displacement at the end to half of its original value. So we want a force that can reduce this displacement to half of it. Are we good? So it's simple. We already know that our displacement at D is having the formula PL on what? AE. But now we want to have the displacement. We want half of it and deduce the force. So we can say half of the displacement we have should be equal to PL on AE. So we are making P the subject from this. And we are going to get something like half of 7.5466 10 raised to the power negative 4 equal to PL. Now we are considering the whole bar. The L is for 1.5 over the area and the E, the same area, which is what? 9 times 10 negative 4, the same E, 120 to the power 9. And making P the subject here, you're going to get our P maximum or the P to be equal to 27.167 kilonewtons. We wanted a force to reduce this displacement to half. So you have to half it and compute for the P, the force. Let's look at the next example. Okay, so next example, a bar AD of length L, cross-section area A, and modulus of elasticity E is subjected to this load and P acting at the point that we have the length to be L on 6, L on 2, and L on 3. One, we are to obtain a formula for the strain energy U of the bar. We have to calculate the strain energy if the P is that and that is that. So first, looking at this bar, we have to obtain the strain energy, the total strain energy. That's the A part. And as we know, the total strain energy is the summation of the individual strains energies in the segments. So this, we have about 3 segments. So we have 1, 2, and 3. So the total strain energy will be U1 plus U2 plus U3. But before that, let's find the reaction. Let's draw a free body diagram and determine the reaction at A. So we are going to get this diagram. So I have my P, and at this segment, there's this force 3P. And I have another one, there's this force 5P. So my reaction will move to that end, R. So looking at this diagram, summing forces along the x to be 0, I'm going to get R, which is in direction to 3P, equal to 5P plus the P. So my R is now going to be, this is going to be 6 and this is minus 3. I'm going to get 3P for that. And I know that my total strain energy is going, let's call here U1, call this U2, and call this U3. It's going to be U1 plus U2 plus U3. So what is going to happen in U1? So at U1, which is the same as what? AB. This is AB, C, and D. So I'm going to draw a free body diagram at AB and look at the energy, or look at the force acting, so that I can use to calculate the energy at there. So if I make a cut at AB, I'm going to get this free body diagram where this is my R and this R, and there's going to be another R. Yeah, but I know that R is now what? 2P. So my U1, we know that U1 is always the force square the length over 2 times the area E. But here my force is what? 3P. 3P square, and my length, what's my length for AB? L on 6. AB is L on 6 on 2 times AE. So if I play with it, I'm going to get U1 to be 9 on 12 P square L, like this for the U1. So at U2, what's happening? I have to create a cut to see what actually is happening in the 2. So I'm going to get a free body diagram like this, where this is going to be my P. And since I'm not cutting the joint, I'm cutting the middle, this force is going to play a role. So this is my 3P, and my reaction will move in the opposite direction to that R. So my total force inside the bar is going to be, how do we compute for that? It's going to be R in the direction with P equal to 3P. So R now is equal to what? 2P, like this. Meaning the force induced in what? AB or BC, sorry, BC is what? 2P. And I know my formula. U2 is equal to the force square, which is 2P, multiplying the length. What is the length of BC? L on 2. L on 2 on 2 times AE. And I'm going to get my final thing to be 4P square L on 4AE. So this is U2. Let's look for U3. So my U3, which is CD, if I create the free body diagram, I'm going to get this P acting here and another reaction R. So I can see that my R is equal to P. R is equal to P. Therefore, U3 is going to give me P, the force square, multiply what is the length of CD, L on 3. L on 3 over 2 times AE. And I'm going to get U3 to be, yes, what's U3? I'm going to get P square L on 6 AE. So summing all the UT, which is U1 plus U2 plus U3, I'm going to get UT. Let me try to sum them up here. 9P square L on 12 AE plus 4P square L on 4 AE is like 1 plus P square L on 6 AE. When you play with this is going to cancel, giving 1. This will also be 3 on 4. So it will be 3 on 4 plus 1 plus this. Total is now going to give me 23 on 12 P square L on AE, like this. So meaning the formula for the strain energy in the bar is 23 on 12 P square L AE. So the B part, calculate the strain energy given P to be 21 kilonewtons, L 1.2, and we have A to be what? 1780 millimeter square, and we have our E to be 70 what? 2 gigapascal. We have to convert the A to what? Meters, and it's going to be divided by 1000 square, which is, if you divide this by 1000 square, first the first 1000 is going to give 1.7 times another raised to the power what? 3. Are we good? 1.78 times 10 raised to the power negative 3. So my U total, my strain energy U here, I'm going to obey this formula. 23 on 12 multiplying P square 21 kilonewton square. That square L, and the L given is what? 1.2, or on A 1.78 10 negative 3 by my E 72 raised to the power 9. Therefore, my UT total is going to give me 7.814. Since it's energy, I'm going to get. So we are good to go. Thank you for watching this episode. And we are going to start with chapter 3, which is temperature, stresses, and strain. Subscribe to the channel and like the video. Thank you.